To live in Dubai during the summer is to endure a climate actively hostile to human biology. When ambient temperatures regularly climb past 45 degrees Celsius, air conditioning stops being a luxury. It becomes a matter of basic survival. Keeping millions of people safe from that extreme environment requires a staggering amount of power. Over 70. The idea is to capture that 45-degree waste heat venting out of buildings during the day, store it, and then use that trapped heat to spin turbines and power the grid at night. On paper, it addresses two massive problems at once. You remove the heat polluting the outdoor air during the peak of summer, and you create a stockpile of thermal energy to replace the dying solar panels after dark. Making this machine work requires pushing the laws of thermodynamics to their absolute limit. The first hurdle is the sheer scale of the temperature gap. To store heat efficiently, you need to take 22-degree indoor air and artificially force it past 400 degrees Celsius. Trying to achieve that kind of lift with a standard commercial compressor would melt the equipment almost instantly. This graphic maps out how we bridge that extreme thermal gradient. Instead of one massive jump, the system forces the temperature up through a cascaded heat pump divided into 3 distinct stages. The lower stages rely on standard refrigerants to reach about 140 degrees, but getting to the top of the thermometer requires specialized working fluids, like supercritical carbon dioxide, paired with an enormous infusion of surplus daytime solar power to finally break the 250-degree mark. Once the heat is pressurized, it needs a place to go. The United Arab Emirates happens to sit on an infinite supply of the perfect thermal storage medium, pure silica sand. It is completely chemically inert, costs essentially nothing to acquire, and easily holds heat well past 1,000 degrees Celsius. The ultra-hot fluids travel through a complex grid of manifold piping, injecting this concentrated thermal energy deep into an insulated underground silo packed entirely with sand. By brute forcing low-grade building exhaust up the thermometer, engineers can successfully construct a massive glowing thermal vault buried safely beneath the desert floor. When night falls, the cycle reverses. A fresh fluid extracts that trapped heat from the sand, lasting it into a rapidly spinning supercritical CO2 turbine. The turbine drives a generator, feeding high-voltage electricity directly back into Dubai's grid. The daytime heat has successfully transformed into the exact power needed to keep the city's air conditioners running through the night. This flowchart demonstrates the system's round-trip efficiency, which is the ultimate test of any energy storage concept. It asks a simple question. Out of 100% of the energy we put in, how much actually survived the journey? Here is where the math breaks down. The sheer electrical cost of lifting temperatures that high, combined with the natural thermodynamic entropy of running a heat turbine, means you lose over 60% of your initial energy. The net round-trip efficiency tops out at roughly 35 to 45%. The mathematical reality of losing 60% of the energy on every cycle places a steep thermodynamic tax on the project. It forces the system to compete with simpler storage methods that carry far lower operational overhead. If the goal is to cool a desert megacity without wasting power, there is a far superior engineering philosophy. Instead of forcing heat up a thermometer to generate electricity later, you store the cold directly. This is achieved through centralized district cooling networks. During the peak of the day, surplus solar power is routed directly into specialized facilities to freeze massive tanks of water and phase-change materials. Dubai has already scaled this physical infrastructure across its most dense districts. Entities like Empower operate centralized plants that serve entire blocks of skyscrapers from a single high-efficiency hub. Because this process keeps energy in its thermal form, rather than converting it back to electricity, it avoids the massive efficiency losses of a turbine. With high-performance insulation, the only real costs are the minor electricity needed for pumps and the slow seepage of ambient heat into the tanks, leaving 90% of the original cooling potential available for use at night. By bypassing the thermodynamic conversion cycle, direct cold storage serves as a far more effective battery for a high-temperature environment. But temperature is only half the equation. Because Dubai sits right on the coast, half of an air conditioner's energy is spent simply removing heavy humidity from the ocean air. To solve this, engineers use solar energy to bake highly concentrated liquid desiccants during the day. The dried liquid acts like a chemical battery. At night, it naturally absorbs moisture directly out of the building's intake air, dropping the electrical burden on standard AC units by nearly half. This leaves the sand battery. While it carries a heavy efficiency penalty when generating electricity, storing 500-degree heat in raw silica is incredibly valuable for direct industrial applications. By heating the sand directly with raw, surplus solar power during the day, that intense thermal energy can be piped straight into coastal thermal water desalination plants at night. It provides continuous, zero-carbon steam while bypassing the wasteful electric turbines completely. This city's long-term sustainability relies on matching storage technology to the specific form of energy it consumes most, aligning raw solar extremes with the direct thermal requirements of a high-heat environment.